All right, so I'm very happy to introduce today Dr. Pietrowicz. She is a senior research scientist in the Applied Research Institute and also a health innovation professor at the Carolina Illinois College of Medicine, as well as affiliate of several institutions, including NCSA and the Department of Electrical and Computer Engineering, and also the Center for Social and Behavioral Science. And so we are very happy to have Mary today to talk about her work that she also to some degree started to work on with collaboration with NCSA on automated detection of disease using expressive human signals. So Mary, let's take it from here.
So today I want to talk about specific AI and human challenges involved in using expressive human signals such as speech, language, movement, and even creativity as a way to screen for disease and monitor a person's state of wellness. So this field has been quietly emerging, but now it's accelerating and doing so with the popularity of AI. I want to provide an introduction to some of the work that's being done in this space, define a problem, get people thinking about the kinds of things that can be addressed with this technique, and even thinking about some problems that would be interesting to collaborate on, because this is a truly interdisciplinary work. No one can do this alone. So I'll introduce the problem space, talk about a few completed and ongoing projects, talk about some of the challenges with this kind of work, and talk about where it can go from here. So to introduce the problem space, I want to ask a question. What if you could determine something about a person's health and wellness status by listening to how they speak, analyzing what they say, watching how they move, or exploring what and how they create? What if you could do that? Then how do you do that? That's the central question of this research. The spoiler is, in many cases you can, and you can do it earlier than human eyes and ears can. Systems that do this are health mirrors, and they provide computer-aided diagnostics or computer-aided therapy support. Now, if you can use things like speech, language, movement, and creativity to know something about health, then the question is, what kinds of health conditions are best suited to this approach? In big general terms, that's anything that affects neurological function, cognition, anything that affects sensing, anything that interferes with the ability to move and speak. And here's the kind of the 6 big areas in medicine that are really great candidates for this work. It's neurology, psychiatry and psychology, cardiology, pulmonology, gastroenterology, that's the upper GI, and speech language pathology. So if you have the ability to do some rapid screening and do it online with AI techniques, and if it's potentially more sensitive than human eyes and ears, or that fill in the gaps when specialized knowledge is required to catch these diseases at early stages, then that's a win. So let's bring this out of the clouds and really look at a list of diseases in these big 6 areas you can target by examining just speech and language alone. So let's look at heart disease. That's the #1 killer in the US. COVID-19 has recently been the #3 killer. Other chronic respiratory diseases are the #6. Depression and anxiety alone affect up to about 30% of the population, especially on the heels of the pandemic. And that's the #1 cause of disability under age 40 in our population. 1 in 9 people over 65 has Alzheimer's. That's slightly over 10%. So that's about 5.6 million people in the US. About 500,000 people in the US have a Parkinson's diagnosis. And about 20% of people in the US have a GERD, that's gastroreflux, which long-term could lead to something called Barrett's esophagus, which is precancerous. About 5 to 10% of people have a communication disorder at some time in their life. And that's just looking at speech and language as a mirror. So that's an opportunity. Now let's have a look at our current healthcare system to see some of the barriers to getting care and getting a diagnosis. Patients often will face a huge brick wall when trying to access the system. And there's been some studies out there to determine what these barriers actually are. And according to one of these studies, the first barrier one might have would be perceptual, just knowing that you've got an issue that needs to be looked at. That's not unexpected. That's very common, say, for example, with mental health. The next area is attitudinal, and those are things like stigma. That's also a really big problem in the mental health area, or just lack of trust in the healthcare system. Then you get into all the structural barriers that are just, how our system works, especially here in the US. Cost is an issue. If you're rural, transportation can be a big issue. Just getting scheduled, if you're a working person, sometimes it's hard, to get time off. Navigating insurance and just plain lack of providers can be an issue. Then if you've managed to clear that hurdle, you get into the office with your clinician, you may experience some other kind of barriers. And one is that sometimes those point of care providers are going to miss things that aren't extremely common just because they don't see them, or because the symptoms are so subtle that they're just not kind of available to human eyes and ears, but they could be available to AI. And so this is given an approach like being done here. Many of those bricks can be addressed with these automated screening tools. So prior to the clinical visit, if you have these easy access online tools, apps or wearables, that can help make patients aware of problems they don't perceive. What you need to do then is speak, move, or provide some kind of creative input. And with speech, this can even happen on the phone. Apps can bridge these gaps regarding stigma. They aren't people, they don't judge. With this approach, your screening services are also available online or in-app anytime, and they don't require travel. They also bridge the gap when there's not enough providers just to screen people, so you can reduce wait times and prioritize people that actually might have some immediate clinical needs. In clinic, these signals function just like vital signs. So the idea is to have somebody speak and move, and they function just like a blood pressure reading. This is also effective in helping doctors see things that maybe that doesn't walk in their door every day, or that are just subtle and kind of under the level of human perception. So the primary of this mission of this work is really using those human signals like speech, language, and movement, and even creativity to build these AI tools that can do this automated, cost-effective assessment of various kinds of health states. If you break this down into research spaces, you'll see that you've got some symbiotic spaces. First you have just the AI systems that support automated health assessments and delivery of therapy. But if you're going to do it using these expressive signals, it's really a good idea to delve into those signals and understand how they function, so you can model them and then feed them back into your disease screeners and your therapy support. If you do that, then your models are going to function better. So that pretty much sums up the approach. That gives you an overview of how this works. To convince you that this is possible, I'll talk a little bit about a few completed and ongoing projects that are in various stages. And I'm going to focus, for this talk on speech and language, and how those signals can be used to build AI models that infer different health states. So first I'll discuss a project that uses acoustic analysis to detect the presence of ALS, that's Lou Gehrig's disease. This project produced some brand new machine learning models for detecting the disease, which did not exist before, and which also discovered some very clear acoustic markers, acoustic features strongly linked to the disease. That was new. This project was done at IBM Research in collaboration with two different ALS groups, the ALS Association and Prize for Life. In the interest of time, I'm not going to play all of these recordings. I'll just kind of describe what this does to speech. If somebody has ALS, you lose control over your articulators, all the muscles that are used to produce speech. You lose control of the velum and you become more nasal. Your speech becomes less precise. Everything sort of slows down because it's more difficult. Your utterances are shorter. You can have unstable voice quality, and you can be hoarse because it's very hard to produce speech. And your whole expressive space just shrinks because, again, it's really hard. We had subjects for this read about 3 sentences or a paragraph. We had approximately, it gives you about 200 utterances. They were balanced between controls and gender. overall, the male speakers were a little healthier, and so the clinical score for measuring how severe the ALS cases were higher, and so you can see that we were able to produce a very simple linear SVM classifier that could detect the presence of ALS in males and females just around 80% of the time, slightly north of that for females and a little bit less for males. You can, when it came down to looking at what the actual acoustic markers were, we saw that a single feature, this was using the RASTA filtering. So RASTA filtering has the effect of highlighting kind of sonic edges. So if you want to draw a visual analog, it's like if you have a picture and then you take a marker and you kind of draw it all around the edges. That's what RASTA filtering can do for you in sound. It also tends to suppress those components in the frequency spectrum that are varying at different rates than you get a typical speech. So this is isolating differences in the quality of the voice, the stability, and in the articulation. So as far as our goals for the project, yes, we were able to identify distinctive features that allowed us to pick up automatically in AI whether somebody has ALS at various degrees of severity, and we were able to actually produce the models to do that. So now I'll jump into another project. So that was an example of a case in the neurology space. Now I'm going to go into the mental health space. So here we're looking at, can you detect the prodromal state for schizophrenia? So that is, are you at risk for developing schizophrenia? And you determine whether you're at risk by having a clinical evaluation that takes, you have to go into the office, have a session with a psychiatrist. It takes some time to produce this diagnosis. We came up with a technique that takes about a minute, and it can be done online for screening. So this is a brand new analytic technique, and it analyzes something called verbal fluency data. So that's a very common test, in psychiatry and in neurology. In short, it's a name, a list of words given some direction. We came up with a new multi-dimensional metric for measuring this, and it's a phonemic similarity metric, which measures the similarity in sound across the speech sample. So this is a brand new way to detect that schizophrenia condition. The technique itself transfers to other diseases because it analyzes, it provides an analysis technique on a common test that's used in many neurological and psychiatric conditions. And because it's, again, it's speech, you can deploy, it's deployable remotely, and it's got some wide-ranging impact, and it's also potentially something that could be deployed in business. So if you're not familiar with what schizophrenia does, a person with schizophrenia may have just some weird behavior. Their speech is a little strange. They may perceive things that aren't there, and so have a decreased ability to understand what's real and what isn't. And their thoughts become less coherent. Their affect kind of may flatten. Their emotions may seem to sort of flatten out. And when they speak, they may jump from topic to topic in an unusual way. Just as an example to describe how this works, they may be talking about breakfast and describing their wonderful pancakes they had, and then they may switch to some seemingly unrelated topic like pandas or pansies. Well, those things have nothing to do with breakfast. They have nothing to do with pancakes, but what they do have in common is the P sound. So the mind, would hear the P sound and anchor on other things that are related to the P sound instead of the concept behind pancakes or breakfast. So the part of the diagnostic process for schizophrenia often includes a verbal fluency test. Psychiatrists will give a person who they think has schizophrenia this test, It measures fluency in terms, you can do it semantically, in which you ask somebody to name as many animals or some other categories they can, and they've got a minute to do it. Here's an example prompt. I'll just read it really quick. It says, tell me the names of as many animals as you can. Name them as quickly as possible. Any animals will do. They can be from the farm, the jungle, the ocean, or house pets. For instance, you could begin with dog, and then you say, ready, begin, and they go and they have a minute. The phonemic test, phonemics again is sound related. You do the same thing, but then you ask for words that begin with a sound or a letter such as FAS. That's the classic test. It's a minute. What happens here though is typically a psychiatrist will do hand analysis. They'll count words. That's the big one. And then they might look for groups of words that begin with the same sounds, like clusters, and then switches between those similar groups of words that begin with the same sounds. So you're analyzing, how do sound similarity come out in a stream in order. But this is laborious to do by hand, and I think we can do better than that with AI and with software. So the research question here is, can we, use the semantic fluency task to identify people who are in that at-risk category? They've done it before with people that have it, but not with the at-risk case. So this is new. And then can we apply, the sound analytic techniques to semantic data, which is kind of counterintuitive, to detect this state. So this is typical, but this is our data set. Typically, when you work with a clinician on a brand new topic, either they will give you some small amount of data that they may have already collected, or you might get to have a conversation about how data is collected. But the point is the data set's small, and you do some limited experiment to see if you can find a signal. So our data set had 36 healthy people, male and female, and 53 at-risk people. They were all native English speakers, but they were from different cultures, different accents. So we had an Australia contingent and a North American contingent. They had the animal naming task, name as many animals as you can in a minute. And a couple of things I'll say, they were all treatment seeking, voluntary, IRB approved. And they were all evaluated with a structured interview for psychosis risk, which is how they evaluate somebody for being at risk. And it's called the SIPS-SOX test. So to answer those questions, I created some machine learning models using, these three different kinds of analysis. So first of all, looking at overall, given, what they gave us, the words, how similar is the sound across the list, independent of order, and then look at the order and see how that's affected. So those are looking at those clusters of similarity and how they switch, and maybe there's another cluster. So independent of word order, dependent of word order sonically, for similarity, and then looking at the semantics, the underlying meaning. So what you do there is you compare the language or the words they give you with some underlying anchor concepts and say, well, their speech, is this close to a particular idea, and then model all these things, build some, classifiers. So just to give you a very quick idea of what this looks like, you want to get the sounds, deployed and mapped onto a graph, and you can analyze the graph and the things in it. So let's say you have a list of words that begin with S. At the top level of the graph, you would have nodes that would contain words that begin with the same first sound. And so in this list, you have on one side, you have the list of words that begin with S, that sound, and then you have this sh. Because you told someone to use S, you can get multiple sounds because of blended consonants. You go down the next level, you have clusters of things that begin with the same two sounds. So sand and sandals. You go down one more level, you get lists of things that begin with the same three sounds, and so on. So the structure is represented by a vector of 37 features characterizing this graph content and the complexity of the content within it. Do something a little sort of similar for phonemic information. Here you're looking at characterizing it in a similar way, but taking into account the sequence. So you're looking at characterizing in order. Let's look at this particular example. You have sea, seaside, seahorse. They all begin with the same two sounds, and then they start talking about sand and sandals. Those are the two different sounds. So you would characterize the clusters that you have of similar sounds, the switching and the continued clusters, and you would then build a phonemic sequence vector representing these, using the 30 features to summarize how those clusters and transitions function. And you do it, with 1 sound, 2 sound, 3 sounds, and so on. Now that I have this promising feature set, I took a complete feature vector versus ground truth, built some classifiers. Again, this is small data, little models, and found that these nonlinear classifiers work very well. And we were able to pick out the folks that were at risk or in that prodromal state for schizophrenia around, over 80% of the time. So that's very good results. We also found that if you build models that focus on phonemically similar groups of people, like separate the North American versus the Australian contingent, the rate goes up. That's not surprising, but that's something that's good to know, is moving forward with this kind of analysis. The last kind of analysis we did was semantic analysis. So we used the GLOVE tool. We computed the global vector representation for groups of animals. It was an animal naming test. So what kinds of animals do you have, the big categories, and then compare the distance between the vector that you got with the words that they gave you and the anchor concept, and measured the similarity by the distance vectors. We did find a signal, but it was a rather weak signal. And perhaps, those animal names really weren't the best category. It was an exploratory studies. What else could you do? Well, you might take some concepts that are more anchored in what happens when somebody has schizophrenia or emotion, or there's a lot of possibilities. So I wouldn't throw this one off the table yet. So we were able to identify people who were at risk for developing schizophrenia using this semantic fluency task, and we were able to build models that could do that pretty effectively. And future work could also, of course, incorporate more free speech, movement, other kinds of signals to truly zero in and understand on what goes on, when somebody's in this prodromal state. So now I'm going to switch to another category that was on our list of the big 6. So now we've got the upper GI condition. So this is, this is gastro reflux. Here, the goal is developing tools that can then detect presence and severity of the GERD condition and also Barrett's esophagus. So if somebody has persistent chronic reflux, something that can happen is that they would develop this condition called Barrett's esophagus. Barrett's is a precancerous condition, and you want to know if you have it because they can treat it, intervene, and then reduce the chances that you'll actually develop esophageal cancer, which can be fairly serious. So this is a potentially life-saving analytic technique. The outcomes are that we think that we can reduce the time to diagnosis, increase our screening accuracy, because sometimes that's not, it may or may not be all that accurate. I have some statistics on that. And we want to be able to build some novel techniques in AI to do this. If you look on the left side here, the technical approach, this is a classic approach when you're building up a collaboration with someone. You need to collect the data set because we're going outside the content of the medical record and data that they typically collect in hospitals. You've got to collect that data set. Zero data sets pretty much exist, for these kinds of things. Then you want to build some sort of baseline machine learning model. Really understand how it functions, try to explain it, look at, play around with the features, get a small amount of labeled data, and then use that, what you learn, to move forward. So the next step is really trying to, build your deep learning models out, get more data, expand the kinds of data that you're analyzing. And it's a very iterative kinds of process. You also have to consider building out infrastructure that helps you do this. and in the context of the collaboration that you've got going. So this is a wonderful group of people. So there's it's a collaboration between Mayo Clinic, University of Kentucky, and Illinois, and it's been supported by grants from Mayo up to this point. We'll talk, so the initial study, the very first pilot study, included some people who were Barrett's esophagus positive. They were, diagnosed to have Barrett's. You get a Barrett's diagnosis by having an endoscopy and a biopsy, and so that's a hospital procedure. We had people that were GERD positive, so they were diagnosed, in the clinic with GERD. People that were GERD negative. So these people they'd had some kind of an endoscopy. We knew that they didn't have Barrett's. We knew that they didn't have GERD, but because they were in the clinic for various reasons, all kinds of reasons, their voices that's very noisy theta. You've got all kinds of other things going on that affect, can influence voice. So that's a very noisy signal. Then finally, that's one control group that you have. The second control group was one that was vocally normal. So these people were evaluated and screened for being a sort of a control group for voice analysis, but we think they did not have GERD, or Barrett's esophagus, but they were not tested in a clinic. We don't know. Statistically, about 5% of that group could have Barrett's and not even know it. So another thing was that they weren't really well age matched. It's just kind of for the first pilot, it's what we had. They were given some speech to read. One of the classic passages, it's called the rainbow passage. You get about 25 to 45 seconds. We had professional recording equipment. So that's the Tascam and the AKG. Models we developed included, we used an open smile feature extractor, which is a good classic feature extractor for audio. Framed it at about 60 milliseconds with a 10 millisecond advance, balanced the models. We're very careful to make sure that we kept all the speech, each speaker either allocated to a train and test group, used bifold nested cross validation with recursive feature elimination, and reported an F1 score. And you can see, it looks like we're definitely picking up on a good signal. So we're looking at the Barrett's versus and the GERD, both of them versus the normals. We've got a very strong, looking signal there, upwards of about 80. And if you look at the noisy signal, we've still got a signal, but it's a weaker signal. So this makes us want to take another pass through here and take that apart. But we've even got a signal showing up in the noisy data. So now that that was the first pass through. Now we're taking a look at recording procedures and how these recording procedures can affect your measurements. And we know that by using different microphones and different recording environments that you're going to get different results. And what usually happens is when you're working with someone, they'll want to say, well, can't you just go out on the internet and have people use whatever recording device they have. And there's an advantage to doing that, because then you've opened up your sample and you've greatly reduced the difficulty in recruiting and collecting data. But you are also introducing a whole lot of noise and issues into your data. So we're trying to just demonstrate what this means. So we're trying to we wanted to run a study that would do a little bit of comparison and quantify that effect. Looking at, again, a group of Barrett's positive people, male and female. I should also say that Barrett's is a male, primarily a male disease. Women get it too, but it's much more common in men. We had GERD positive, GERD negative, and vocally normal. This time they read the same passage, but same duration, but for all but the vocally normal recordings, which was a legacy data set, they were recorded simultaneously with professional equipment and an iPad on the desk with an internal mic, nothing, no external mic support. And so, as you might expect, those iPad recordings were much noisier, but could you still work with them? You could, but let's look. if you look at the impact on the measurements that you're taking on that audio, you see that on the left, you have professional equipment, on the right, you have that iPad. You're getting some different ordering, you're getting some different features, and the green highlights the things that are the features at the top. You know, I just cut it off for demonstration purposes here, 17. Okay, now let's take those apart a little more and examine just those common ones. And we see that many of the features track pretty well. All right, there's subtle differences. So, you know, if you see the MFCC SMA2, that's subtle, right? But look at the one on the top left. That is the harmonic to noise ratio. So you've got how the part of the signal that's regular. So in a typical voice utterance, you'll have the fundamental frequency, which is around, you know, sort of kind of connected with your perception of what the pitch is, and then you'll have integer multiples of that fundamental. Noise can be it's irregular. It tends to be at high frequencies. It doesn't have that regularity pattern. And what we're seeing is, yeah, there's definite differences there. That's not a terribly big surprise, but it is interesting. You know, it's interesting to be able to quantify it. So, and as we said, these recordings were notably noisier. The features, you know, that are sensitive to noise are going to vary. The ranking is going to differ. Your models, if you're not careful, never, for example, take one condition, you know, and record it on one kind of equipment, and then use a different kind of recording equipment to record your other condition, because then you're going to learn noise patterns and patterns that are, you know, just different in your due to your recording environment. So you've got some options. You can try to standardize your recording processes, which may or may not be okay for you. You can clean the data, which maybe, you know, that's destroying some of the information, but you know, you can also use some AI techniques to help bridge that gap. You can augment the data with noise to make your models more robust, and simulate the kind of noise that you might be getting in, you know, across different environments. And of course, you can always increase the size and diversity of that training data to make those models more robust, no matter what kind of models you're using. Sorry about that. The question, can we detect Barrett's esophagus via machine learning techniques and applied to speech? This is a second pass through, a second pilot study. Same question, but in this case, we're focusing in on the males again, because that is in this particular clinic, they had a very high rate of male patients. Again, the disease is more prevalent in males, and so for this pilot study, we focused on males. These were age similar, matched in age, unlike our first data set. We looked at the Barrett's esophagus as being present and active and visible, versus they've had Barrett's, but it's currently not present. It's been treated. So that's a second category. And they still have the underlying GERD. It's just been treated. We have a GERD negative category, which has been, now it's a little more, I guess, sanitized for confounding conditions and vocal normality. And then we have our control group. Then these are vocally normal. They've been screened for not having GERD symptoms, but they did not have a endoscopy. They did not have a biopsy. We actually don't know the status, and we could have up to about 5% potentially of Barrett's esophagus in that sample. Red speech, same procedures. We looked at, again, still got the kind of small data set, looking at classic models, same feature type of feature extractions, basically the same process, but here we cleaned up the sample. And what we found is that we successfully were able to distinguish that Barrett's esophagus present or not present, both of those conditions, from controls and from GERD negative. What we found here, though, is, in this second pilot model, that looking at the summary conditions, the statistical variations, and so on across the entire sample functioned very well. Whereas if you just take a broad swath approach and look at individual frames across the sample without any regard for the ordering and the effect, that sort of highlights the importance of looking at that ordering and effect for the future kinds of models that we're going to build. And we see that, yes, we were very well able to distinguish both whether somebody had Barrett's active or whether they had Barrett's treated. Looking at some of the kinds of features is interesting too, because I'll just sort of highlight a few points here. Spectral entropy is something it's a measure of randomness in the signal. Randomness in the signal is associated with noise, so you're picking up on different noise characteristics, some of which could be related to maybe irritation and hoarseness. The psi sharpness is another. It's a perceptual measure, and it's based on the amount of high frequency components in a sound. So screechy and high is high psi sharpness. Again, it's sort of associated with noise. You're getting up into that high frequency range where the voice doesn't normally lie. The centroid is where most of the energy in the spectrum is. Again, that's could be picking up on high frequency components again, and also highlight that percentile. That's really zeroing in on the number of values that are less than or equal to that bottom percentile mark. So this is sort of pointing, in the direction of how irritation or that Barrett's esophagus lesion. I don't mean a cancer by using that word, but yet it's a precancerous condition, can affect speech. So again, AI can hear what human eyes and ears may miss, because this is not obvious to human eyes and ears, in the sample. So what we're doing, we're continuing this work right now at looking at an expanded scale, a broader range of speech samples and speech types, different kinds of speech, and are currently working on some deep learning models. I can't share them at this point. We haven't published on them, but that's where we currently are. Now I'll segue into another type of data. This is voice and speech disorders. Here we're looking at tools, again, that can detect the presence of voice quality and voice and speech disorders and build environments to support those therapies. So that's the overall goal. This is another wonderful collaboration, but with the voice team at Mayo Clinic and University of Kentucky. The clinical folks are helping provide the clinical expertise, patient population, data collection, and some acoustic analysis that's common in the speech language pathology world. Illinois is focusing on building the machine learning models. Technical approach is again, it's very similar. It's this iterative approach where you start with small bits of data and continue expanding, exploring models and iteratively for improvement in understanding and explainability. The questions here for our pilot study, our first pilot study, was automated detection of a clear versus habitual speech. Clear speech is something speech language pathologists do to help somebody that has a disorder become more intelligible. So it's a hyper articulation. You might, if I have the word cat, cat, that's a how it might come out in clear speech. So it tends to be hyper articulated consonants, separation, things get louder, and the rate slows down because it takes more time to produce speech that way. So being able to make that distinction, in a tool can help you build tools that either provide therapy or that help you determine whether somebody has a disorder. So again, we have both males and females with normal speech and with mild to moderate dysphonia, which is a speech language pathology condition. And the subjects were similar in age, so that, we weren't going to pick up on any speech differences just due to age. Here we had read speech again, but there's something called the Kate V sentences, which are designed to bring out, to get somebody to elicit a detectable problem in speech language pathology. It was recorded with professional equipment. Here again, we, starting out with that explainable approach to try to, see if we can find the signal, balancing our conditions, same type of an approach. We were able to definitely find a signal. So looking at just straight up acoustic analysis of common speech language pathology features, we see that, as somebody, the differences between habitual speech and clear speech were very trackable. These are common features that they look at. This is a cepstral peak prominence. You can see it increases when somebody produces clear speech. Same thing for their alpha ratio feature. And then if you look at also speaking rate, you can see that goes down. That we didn't see the effect really in the males, and it's probably due to perhaps the kind of instruction that they had. Speech language pathologists in our data collection sample instructed many of the females, whereas they were not instructing a large group of the males, which came out of the GI clinic. So we might see some differences, possibly because of that. And in general, people become, when they try to utter things in clear speech, they get louder and more intense. Looking at our machine models, our pilot models show that, yep, we were able to distinguish clear speech and habitual speech. And this is looking at samples from the same speaker. So you're actually getting at, you're zeroing in on what those differences are in the speech. And we see that, not surprisingly, our summary features again perform better than those frame level features because they were extended across the whole entirety of the utterance. The better female performance is likely the result of the better instruction that a segment of them got during testing, because they were instructed by speech language pathologists. If we separate the models and look and see if we can distinguish clear and habitual speech in dysphonic speakers, and then build a model for that, and then build a separate model for normal speakers, we see that we can still detect the differences in the dysphonic features and in the normal speakers. It's a little more difficult to make that distinction by about 6 to 10% in dysphonic speakers, which is not an unexpected result. If we try to explain those results, the sample features will back up the intuition. So again, with hyperarticulated speech, the clear speaking style, you're getting a lot of emphasized consonants, a lot of, at the beginnings and endings of words. So we see this, again, the difference in the harmonic to noise ratio is different between the two kinds of speech. You can see that the clear speech has a lower level of harmonics than the habitual speech because of all the noise generated probably by these hyperarticulations. Looking at the frequency band between 1,000 and 400, that's where you find a lot of the higher formants and noise, frankly. So you're probably picking up on differences in the noise levels again by the two speaking styles. The length element norm is when you sum up the vectors of all the frequency components in your signal, and so you're probably picking up a lot of higher frequency noisy components. And your zero crossing rate, if you've ever seen a waveform, just oscillating around a zero, higher frequencies mean higher zero crossing rates, which mean probably relating to noise. And you can see at the end here this min settling. So the underlying segmentation that happens, it's picking out the smallest segments, right? And the smallest segments correspond to the hyperarticulations that you see at the start of words. And just for intuition, I flipped it and I did I tried to separate dysphonic from normal speech during both clear and habitual speaking styles. And what you can see is that it's about, when somebody is dysphonic, it's about 6% harder to detect that habitual, or I'm sorry, when somebody is, it's about 6% harder to make that distinction when somebody is speaking in a habitual manner versus a clear manner. And very briefly, I'll touch on the last project I'll touch on is our automated detection of depression and anxiety. And so here we're looking for tools that can detect the presence and severity of depression and anxiety via automated analysis of voice and vision. So we're looking at the big picture is to look at, yes, looking at speech, but also looking at movement, gesture, expression, emotion, quite a large collection of features. It's truly multimodal. And so this is a collaboration across UEComp, that's our clinical partner in Peoria, is at University of Illinois College of Medicine, NCSA here. So we've got our NCSA faculty fellows group, and also University of Illinois ARI, all working together on this project. Very similar kind of an approach to doing the analysis here. Our data collection goal is 160 speakers, and we're looking at people that have that screen positive for both depression and anxiety at all ranges of severity. Depression only, again, all ranges of severity categories, anxiety only, and then controls. They've been screened for confounding conditions. For example, if somebody has Parkinson's, they're excluded from the study. Our data includes a 30 to 40 minute standardized interview, along with some standard screeners that are used in the field. So the PHQ-8, GAD-7, K10 are depression screeners, anxiety screeners, and a general mental health screener. We collect custom demographics, medical history, and medications. So we've got kind of a big picture of what's going on with someone. We give them the verbal fluency test, the naming, 1 minute long naming tests. They're both audio and video recorded. And this data set's consented for future use. So we've made sure that we can use it and build on it in the future. And also for the curation of a public research and education corpus. It's a resource that we just, that's just not out there. Data collection is to have a screening process automated on RedCap that will tell you, whether someone's in or out. You can recruit online for that. And then once they're in, they complete the survey instruments, the interview, and the verbal fluency data. It's been collected online and in person. We started out in person exclusively, but then ran into the pandemic and some other issues, just logistics with the clinic, and have switched mostly to an online kind of a format. We've got a HIPAA-capable system that uses a combination of AWS, NCSA Nightingale, and an IRB-approved protocol. So that's a whole nother, that's definitely an aspect that when you're doing a project like this, you have to design. The analytic approach is a very similar exploration of the data set, iterative exploration of these models, and increasing, starting with explainable ones that's small and increasing into the more deep learning kinds of models. We want to be able to fingerprint phenotypes of depression and anxiety, and I've got another. I won't go into the technique here. We don't really have time, but you can use crowdsourcing to describe and then infer different classes of expressive styles and correlate them to phenotypes. Curate this data set, and we also want to take this data and the models that we're collecting and deploy it into the NCSA Clouder system, so that we better support our researchers in this space going forward in the future. So the final topic I'll talk about very briefly is just the barriers and challenges, and I want to do this because Sometimes, when you get kind of two extreme reactions. One is that, oh my gosh, it's magic. You can do everything with it, and it's kind of a magical approach. Well, there's a lot of issues. And the other one is, if you're aware of what some of the issues are, oh my gosh, this is never going to work. So it's really neither of the two. But just the rhetorical question is, what do you think the number one barrier to this kind of work is? And the spoiler, guess what? It's data. So just the availability of these curated and labeled data sets. You have recruiting challenges. You need to try to automate this pipeline. You want to make sure you engage the user. You don't, or the participant. You don't lose them. You've got IRB issues and the whole data labeling kinds of questions. Without data, you really, you've got to have data before you can get into things. Oh, and the second issue is data. So you need a lot of data diversity. You need to think about that context, the costs of data collection. And this one in blue, this bullet in blue, this is my heuristic. In general, if you have about 100 speakers, 100 really good samples, you have a demo in a paper. It's not production. Even though statistically you can do something with that number of samples, but practically you have a demo. If you get into the high hundreds, maybe thousands, then you've got a pilot. You've got something that you can effectively try out. But production, you probably have to go up another level of magnitude or scale it out further. It's not the path to getting something production is not in the small, less than 100 kinds of samples. And it means that you're really getting into multi-institutional types of projects. And I'll just kind of spoiler here. We've got data security, equipment kinds of issues that we touched on already. You've got to really think through your computation environments. You've got to make sure that you can do all your computations in a secure kind of environment, in a way that you can share storage, federate things, and draw on some high computational power when you need it to build and update those models. It's a very interdisciplinary space. You want to be able to share data, go multi-institution, have that consortium mindset in your head, because you really need to collaborate and navigating that clinical approach and integrating it with the engineering approach is what you need to do for this whole type of work. You've got to think about comorbidities. For example, something like depression occurs with a lot of other things. Depression and cancer is very common. And how do you navigate that? So dealing with potentially confounding conditions that's a very real thing. You need to be able to characterize and profile things like the voice, movement quality, such that you can deal with it on a kind of a vectored approach, a fingerprint approach, to characterizing it and modeling it. Then thinking about how you might take that signal or that kind of data and integrate it into a medical record. That's all before you get to all of the usual AI questions about explaining things, dealing with federation, dealing with multimodality, data sparsity, longitudinal analysis and prediction, and many of those things. So, and the last thing is the application context. Whenever you're developing an app like this, you want to make sure you target it at the people who are going to use it. So you've got clinical needs, and then you've got, say, end user, commercial user kinds of needs, and making sure that when you're building an app, that you really direct it at the customer. With that, I've gone through several projects, talked about the general approach, talked about why it's a useful approach. And with that, I'll open it up to questions. If this has gotten you thinking and you have questions or want to explore collaboration, please contact me.